Thinking Machines Lab just published the full weights to Inkling, a 975 billion parameter foundation model available right now on Hugging Face. The release comes with rigorous performance validations. Inkling scores 97.1% on AIM 2026, hit 77.6. This exact balance of mathematical scale and computational sparsity allows engineers to own, run, and customize frontier-class models locally on their own infrastructure. The exact hardware footprint of Inkling comes down to two numbers. It stores 975 billion total parameters, but uses only 41 billion active parameters to process a single token. To isolate a single MOE layer, as a token passes through, the system restricts active pathways. Out of 256 available routed experts, exactly 6 are activated. These are supported by permanent pathways, 2 shared experts that remain active for every single token. The mechanism selecting which 6 outer nodes to activate is a sigmoid-based router. Traditional routing architectures force load balancing by applying strict penalty losses during training. Inkling abandons this method completely. Instead, the router integrates an auxiliary loss-free bias. This keeps expert utilization evenly distributed without corrupting the primary training objective. The data processed by the 6 routed experts and the 2 shared experts is then normalized jointly and weighted to form the combined output. By locking the routing topology to this precise 6+2 configuration, Inkling retains the emergent reasoning capabilities of a massive parameter space while restricting the hardware tax to that of a mid-sized dense noddle. Handling massive sequence lengths, specifically scaling up to a 1 million token context window, requires a redesign of the model's memory architecture. This diagram illustrates the specific distribution of attention layers engineered to process that massive context efficiently. The network interleaves 5 sliding window layers for every 1 global attention layer. The researchers also pivoted away from standard rotary positional embedding, or ROPE. They opted instead for relative positional embeddings to encode location data. This is supported by the addition of short convolutions placed strategically immediately following the key and value projections in each attention layer. Relying on relative embeddings and enforcing a 5-to-1 attention ratio directly solves the mathematical degradation of recall. It allows the model to retrieve exact details across a million-token sequence horizon without dropping data. The pre-training phase required the ingestion of 45 trillion tokens, spanning vast textual archives, complex image datasets, and rich audio and video data. This flowchart maps out the bifurcated optimization strategy required to process that volume of data without mathematically destabilizing the network. The muon optimizer is assigned exclusively to process the large matrix weights within the model. Meanwhile, the atom optimizer handles the remaining standard network parameters. Success at this scale also requires strict hyperparameter scheduling, specifically regarding weight decay. The engineering team mathematically coupled the strength of the weight decay directly to the square of the learning rate. Enforcing this relationship ensures the overall size of the model's weights remains completely stable, even as the training stretches across vast data horizons. Combining the hybrid muon and atom approach with strict weight decay coupling prevents the catastrophic loss spikes that typically destroy models pushed to the 45 trillion token threshold. Following pre-training, the team initiated the final behavioral shaping phase, large-scale asynchronous reinforcement learning. The volume of this RL pipeline was massive, consisting of over 30 million continuous rollouts. This chart tracks the aggregate evaluation reward on complex reasoning metrics across the duration of the run. The reasoning performance scaled strictly log-linearly. The model improved continuously without hitting a plateau over millions of rollouts. During this phase, the training system dynamically adjusted the model's thinking effort by modulating per-token cost penalties directly in the system message. Deep into this RL scaling process, an emergent architectural behavior appeared. The model naturally learned to heavily compress its internal chain of thought to avoid token penalties and save computational cost. Early in the RL process, the model used verbose, highly grammatical reasoning. By the late stages, it had stripped this down to a telegraphic, highly condensed logic flow. This compression maintained absolute output accuracy while drastically reducing latency. Applying asynchronous reinforcement learning at this scale increases benchmark scores while simultaneously training the model to execute logic with maximum computational efficiency. The final physical deliverable produced from this training run is an NVFP4 checkpoint variant. This specific low-precision format is engineered explicitly to maximize inference efficiency on next-generation hardware. The commercial reality of this release is immediate. A model of this magnitude can now be customized directly on platforms like Tinker or deployed via open-source tools like VLLM and llama.cpp. Local deployment bypasses the inherent data privacy restrictions, rate limits, and latencies that come with relying on proprietary black box APIs. This forces a macro-level question onto the AI industry regarding the actual durability of closed-source competitive advantages. The baseline reality of today's landscape is clear. A 975 billion parameter foundation model is freely in the hands of the global engineering community. With a 97% AIME score and a fully open weights release, Inkling transfers frontier-level control from centralized providers directly to local researchers and builders. Synthiq Labs, from research paper to working prototype.